Hi, welcome back to Statics 1. We're going to talk today about simplifying systems, same way we did before with point loads and force couples. We're going to do the same thing now with distributed loads. So we're going to talk about what is a distributed load. We're going to talk about distributed loads on along the x-axis, and then we'll talk about how to simplify them. So just to kind of review, you might remember the topic of simplification involves typically like a beam, and we'll put a hinge, right? And we'll talk about that a little. We're going to talk about this more. These are called supports. And actually where we're heading, and I'll just give you kind of heads up, we're heading towards the calculation of what we call support reactions. Support reactions is kind of important to remember. Support reactions, and so a support reaction would be essentially the response of your system to your applied loads. So we have, for example, some complex system of forces and moments. So there's two forces, we have a force couple. You might remember that we were able to simplify it, and we talked about simplifying it essentially in two steps. The first step is to find a force and moment, and we could do it anywhere, but typically we did it like at the left edge of the beam. And then we could find the distance somewhere else to apply the force at a distance away from that beam, which would be equivalent. So you might find that this complex system has a simplified version, which is just one force at some angle applied at some distance d. You should know how to do this. If you don't, you might want to go back to look at it again. Now we're going to be talking about distributed loads. So instead of these are point loads because they're loads applied at a single point. But now we're going to talk about distributed load. Okay, so now we talked about our complex systems. Now I want to talk about a distributed load and what exactly that means. And what I'm going to show you is essentially like you can think about it as a piece of flooring. So imagine you have some surface area. This is a 3D. Here we are at the surface area, upward in the vertical direction. And we're going to apply a continuous surface representing the downward force on this. And it could be, in fact, that you're representing the gravitational load imposed by the surface itself. It might be a reinforced concrete flooring, and it's imposing a downward force on the beams underneath. So I'll draw that. Well, let me just draw first a number of arrows. Hopefully you understand that the arrows are not representing discrete points where the force is applied, but those arrows would be everywhere on the surface. Essentially, it would be a tiny little arrow everywhere on the surface. And so we can represent that as a surface that's overlying this thing. And it can, but does not necessarily have to be a flat surface. Okay, so that red line essentially represents the downward force on this thing. And the height of it relative to the surface itself would be proportional to that force. All right, so we could call that, we're going to call that height, that downward force, it's essentially a force per unit area. And we're going to represent that as P. You do this in black. Represent that as P, X, comma Y. So that's the downward force and it would have units of, or dimensions of force per unit area. So it might be, for example, like a Pascal, which is a Newton per square meter, or it could be like a pounds per square inch. So it's it's not really a downward force, output downward force per area. So it's like a pressure, essentially, force. Okay, so if it were a flat surface, in other words, if the pressure were continuously constant everywhere, then we would just take the pressure times the area over which it's applied, and that would give you the total force, or the resultant downward force on this surface area. All right, right, now it turns out that frequently we're going to look at systems where the value might change. The value of this P might vary only in the x direction. And we're going to basically assume it's constant in the y direction. So we're going to end up, and actually what I'm going to show you is, we're essentially going to cut out a wedge of this thing. And we could imagine it being like a 1 meter wedge, which would make it really easier. And we're going to call the force, essentially what we're going to do is we're going to multiply this pressure times the width of my wedge, which I'll call B. That's the width of my wedge. And then we're going to come up with something else that's called W, which is going to vary only in the x direction. This one's going to have units of force per unit length. And we can represent W on a beam. Actually, let me do it a little differently. And this is actually kind of easier to visualize and think about. But we'd have a beam like that. We could put our supports here. And hopefully, I think we talked about this. Hinge on one end, roller on the other, sort of a standard technique. And now we can put a W. And I'll do the same thing, just like I did here, arrows. I'll put arrows here so you remember that it's a downward force. Although the arrows would essentially be, you'd want to have like 1,000,001 arrows along this thing, so it's essentially continuous. And then we have our W like this across, and this W does not, the W can, but does not have to be horizontal. This can be a varying surface. So this is what we're going to call W. And that's our loading per unit length. So it's no longer a force, now it's a loading per unit length. Per unit length. Hopefully you see that, so it would have units of like newtons per meter, for example. And hopefully you'd understand that if we multiplied, if it were a constant value, in other words, if W did not change in the x direction, that we could multiply W times the length of our beam, that would give us our total force moving in the downward direction. All right, so now what I want to do is we're going to expand that. We're going to talk, so that's like for a constant W, but we're going to look at the situation where W varies over the length. And we're going to find how we're going to simplify it so we can do just what we did here to reduce down to one point force at a particular location. We can do the same thing for distributed loading. So let's talk about that next. First thing, I'm going to erase the board, and then I'll come back and show you how to do that. Okay, so we're back. I'm back. So what I want to talk about is how to deal with how to simplify distributed loading, so we can represent it as just one force at one location. So let me reproduce the problem that we're dealing with. Essentially have a beam like this, has some supports holding it up, and it has a continuous loading that may or may not be flat. In this case, I've represented it pretty flat surface. This is going to be W of x, but you see I put W of x, meaning that W may vary in the x direction. And I'll just show this as a bunch of arrows downward. And again, we want a simplified system where we could represent that instead of as a distributed load, it would be just one point, one force at a single point. And that would be our simplified system. That's what we're heading for right now. So the first thing to consider is how do we figure out what is that resultant force downward. And we said before that if it was flat, we could take our W, our flat W, multiply by the length, and that would give us our downward force, because of course W has units of newtons per meter or pounds per foot. Okay, so we multiply by length, and then we get either pounds, or multiply by meters, and we get number of newtons in our downward force. But let's think about this a little bit more analytically, because W might in fact vary with X. And if we were to take a little wedge of this thing, like from here to here, and consider it having some width of delta X, imagine that as a width of delta X, and it has some average value of W in here, we might realize that the downward force of this little piece here is going to be equal to, I'll write here delta, I'll write it delta F, so it's like a little piece of the overall F is going to be equal to delta X times W. And if we took a bunch of these little wedges, we could add them all up and we get the total downward force. So I'll put that as F equals, and we could sum that up over all our delta F's like that if you want to be consistent in how we present this. And we'd sum this up over here, and I'm going to switch out, I'll put back in my W of X to remind us that W may vary with X, times delta X. Right, the sigma, that's our summations. That's how we're summing over all the little green wedges. I've only drawn one of them here, but we have a bunch of them over this entire length. As delta X shrinks to infinitely small width, in other words, as it approaches zero, you might recognize that this becomes an integral. And that's where we're going with this. So we'd say, and I'll even put F of R, so this is our resultant force. Remember, we always talk about F of R being resultant force. In this case, it's downward, equals the integral from 0 to L, being essentially from here to here, of W of X dx. Okay, and it would work. We could put, if we put a flat value, let's just test this to see if it works for our flat surface. If we had integral, so this is for a flat surface only. Let me write here, flat surface, where W of X equals just W. I'll make a prime here to help us think with it. So W of X would just be equal to a constant value. So then we can take F of R equals the integral from 0 to L of W dx. And what we realize is that the W is constant, or W prime is constant, we can take it out. And the integral of dx is just x. So that's going to be equal to W x from 0 to L. Right, simple calculus, and now we're going to end up with W L, which is what we said from the beginning. We already understood without doing this analysis that was the case. And what you can also see is that, looking at this, is that of course this integral in fact represents the area under this W curve. So we can look at it, let's imagine we have another loading which is a triangular loading. Here's our beam. We have supports on it again, of course. And here's my W, and this, ignore this little thing here. And I'm going to put over here W max. And so this is my loading. It shrinks. I'll get out of the way in a second. So it starts at 0, and it goes up to a value of W max along a straight line. So we realize that if this resultant force is in fact the area under this curve, this is just a triangle. So it's the area under this curve is going to be equal to 1/2 times the width, which is, if this goes from 0 to L, is L, times W, the height, divided by 2. So this resultant force equals 1/2 L times W max. Okay, where W max, that's the W value at the right hand side where the triangle is at a proportion. So you can see we can just represent, this is essentially what we're looking at, and this is the area under the curve. Okay, so we have kind of gotten to the point where, remember, this is our goal. We have a distributed force. We want it represented by a single force. At a particular point, we know already how to find the magnitude of this downward force. Okay, but now the question is, where do we put it so that it's essentially equivalent? Remember, equivalence from the perspective of statics 1 means that the external supports will have the same reactions that they would with the more complex system being employed. So I'm going to use the right-hand part of the board over here to do this rest of what I was hoping to do now. And let's do the same thing we did here with this little wedge. We're going to do that for the moment. Remember, we need to find, well, whenever we do the simplification, we're going to evaluate the moment over here. So now in this case, what if we wanted the moment, first, when we came over here, we looked at the force at this, resulting from that wedge there, which we decided was delta x times w. In this case, we're going to talk about what is the moment at that location. So what I'm going to write here is, that moment is delta m of 0. If we call this, we'll call this point 0. Delta m is 0 is equal to that same force, w times delta x, times the length from here to here. Remember, we have a moment arm. We'll call this x. And we have a moment arm turning, because we have a downward force, essentially it's applying a moment this way, so it's actually a clockwise moment, so we need to represent it with a negative value, but it'll be the force times that moment arm. So we're going to end up with w, again, of x, times delta x, times our moment arm x. And I put it in parentheses so that it will be separate from our delta x. So again, w is the downward force per length. Delta x is the width of our little wedge, and x is the length of our moment arm. So what we're going to do now is we're going to add up all of these little moments. In other words, moments resulting from that wedge. But what if we have wedges here, 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 and here, everywhere along the length of this thing? Then we'd say that the total the moment at 0 equals the sum, and I'll even use an r here like that. So the resultant moment at point 0 equals the sum of my little moments, which is going to be equal to this summation over w of x delta x times x. Okay, and just like we did before, if we take that delta x, use the width of this green little wedge, we make it smaller, smaller, smaller as it approaches 0, this becomes an integral. Hopefully you recognize that fact. And we can simply write the moment at our point r equals integral from 0 to L, in other words, from the left-hand side to the right-hand side, of w of x times dx. So it looks a lot like our integral for the this one here, which is the area under the curve, which is this is the downward resulting force, which is the integral of wx dx. And this one is the same as before, but now we have wx times x, our moment arm, times dx. Okay, so they're actually very similar, and I'm going to essentially highlight this one, because that's very important. So lastly, so now we know that the moment applied by this w function can be evaluated like that. So finally, if we were to figure out, so now we want to know the length of the d value that will go from here, from that left edge, to this point where we want to apply our single resulting vector. We're going to call this d. And You can think of this two ways. From the perspective of our resulting vector, we would say that the moment O, we'd say that the m of O of R equals the f of R value times D. Okay, so we take the resulting force, although it's in the positive direction. This is causing a clockwise rotation. So it has to be a negative value. In fact, hopefully you caught and you were like concerned about the fact that I did not show the negative values here, which we should. If it is a downward force, we're going to have a negative value here, a negative value here, and negative value there. Start substituting these in. If we want to find the value of D, where f of r and O of r are represented by our integrals, we can start putting them in. So I'll put this in here. I'm going to substitute this over here. So we're going to end up with negative integral 0 to L w x to x dx. So that's my resulting moment using that integral. And I'm going to substitute this integral for f of r to negative 0 to L w of x dx. I have to check my camera again, sorry. I substituted this integral for f of r over here, and then I'm going to multiply this whole thing by d. Remember, d is what we're looking for. We know w, so in principle, we can always do this integral. We can do that integral. And now we want to say, how do we find d? So we can find d by just isolating d on the left-hand side. And so we're going to say that d equals integral w of x times x dx from 0 to L. So here's this value, and we're going to divide it by this value, this integral, w of x dx. And you may or may not realize this, but this in fact represents this integral divided by that integral. Essentially, this is the first moment divided by the 0 moment equals the centroid of our area W. So what we found is that the value of D, the location where we're going to apply this, is always at the centroid of the shape that we form, the shape formed by our W function. So D is at centroid, the centroid. Okay, so that's a really important point. In fact, it's so important, I'm going to put in 2 exclamation points. So the way you do these problems is, first you find the force using this function, or integral. Remembering that it's equal to the area under the curve, and frequently we're going to not actually integrate it, we're just going to take the area under the curve. And then we're going to find D, and you could evaluate the integrals, but frequently we're just going to go, oh yeah, I know where the centroid is, because we're going to use shapes that we recognize. So I'm going to erase the board. I'm going to talk one more time about how to do this simplification process for either like a rectangle, a series of rectangles, or a triangle. And then we'll move on to something else. So I'm going to erase this now. So we talked about distributed loads, and there were kind of 2 take-home points from it. So let me just draw a picture again. Here's my beam. I have some distributed load, W of x, meaning that W, that loading may change in the x direction. W has units of like newtons per meter, or it could be pounds per feet. So we have some downward force, W. And the 2 take-home points from what we talked about is that this is a beam, by the way, is that the downward force, F of R, is going to be equal to the integral of W of X dx, which is the area under the curve. The W curve, W of X curve, may not be a curve, maybe just a straight line. That's the area under the curve, and the location at where this is applied. In other words, we're going to have some F of R value. Let me do it in green. This is my simplified system. Remember, we have a complex distributed loading. We're going to reduce it to a simplified force, and it's going to be applied at some distance d from the edge, and that distance d is equal to the integral of W of X times dx divided by the integral of W of X dx, and that in fact is the same as that, which is the centroid of the area under the curve. And it really is equal, it's the horizontal dimensions of that centroid. Obviously the centroid is, this is like a two-dimensional surface where it's x versus wx. What we really care about is the x value of that centroid. Okay, so these are the two take-home points. So there are kind of a couple of kind of problems that you're going to see. You could see a very complex system, and I'll just do that one first. Here's my supports, and the W could be like a parabola. It could be, and you'll look in the textbook, and you'll see all kinds of different like functions that occur. W could be something like that. Typically, we don't really, civil engineers don't really deal with that kind of a problem. We're going to deal with, for the most part, this is my support. Whoop, I put my hinge on, a roller on the left this time, hinge on the right. We're going to, for the most part, deal with even sort of values where W varies evenly over the length. In other words, W is a constant. So the area under that curve, and we already know this, the area under the curve, remember this is L and this is W. The area under that curve, F of R, equals just W times L. And the centroid of a rectangle is, of course, the middle point. So if we have 0 over here with L over here, L over 2, right, is that going to be the value of D, our centroid. It's going to be L over 2. So that's the first kind of system we're going to see. The other one, and we could certainly, theoretically, might see something like a triangle. And in this case, I think we already talked about it. So the area under the curve, we already talked about what that is. And again, it goes from 0 to L. 0 over here, and I'll do it over here. 0 to L. 0 to L on the other end. So the area under the curve is FR equals W max times L over 2. So W max. And the centroid, we can do it. We can evaluate it using this, but I'll just tell you that the centroid is the average of the x coordinates at the 3 points. So we have a value of XL here. We add that to L there, and then add it to 0, and we're going to end up with essentially 2/3 L. Right. So D is equal to 2/3 times L. Okay, that's the location where we're going to apply that point. So you can imagine that we have our simplified system, and it makes sense that it's skewed a little bit to the right, whereas the rectangular one is in the middle because it's symmetric. This one's asymmetric, so it's a little bit to the right. The other kind of thing you might see is a trapezoid, where we have a system like this. Let me draw, well, ordinarily you'd start out, they would tell you, oh, it's a trapezoidal surface. Here's my W, and it varies along the length like that. And here's my beam at the bottom. Here's a beam with a trapezoidal surface. We could divide this up into two pieces. So instead of ending up with just one force, like we did here, we'll end up with two. And we'll do that by essentially breaking this up to this being the summation of a rectangular surface below this green line, and then a triangle essentially that goes from the green line up to the upper surface. And then what we'll do is we'll find the resultant vector, like this system, we'll find it here, and for this one we'll be essentially here. Instead of having just one force, we'll end up with two forces. But that's simple enough for me, and we can easily use this to evaluate the support reactions. And I told you before, that's where we're heading. We want to evaluate the support reactions that result from some loading force that we're going to be putting on the system. All right, so that finishes up the chapter. Actually, let me show you one more kind of problem. And I know there are homework problems like this, where we have a beam, and we have maybe something that varies. I'll do this. So there's my W values. Essentially, these are forces. And we could do it, we could evaluate these integrals to find the one resulting force applied to some location. But again, just like we did here where we broke it up into two pieces, you could essentially break this up into, in this case, three pieces. We have a rectangle here. So we'd find the area under that curve and we'd apply it at midway between the points. We'd find the area under that curve, apply it at its center, and then we'd find the area under this curve and we'd apply it, again, it's a triangle, so it'd be like 2/3 over. Because you end up essentially with 3 points. And then if you wanted to, you could reduce this to a single point if there was a good, compelling reason to do so. So that's the distributed loads simplification. And we're going to wrap that up. And if you have any questions, let me know, and I'll see you in class.